Up to now, we've talked about resistors and capacitors and other components, and we've connected them up and learned about Ohm's law for resistors. And we've learned some things about series resistors, like we show here. The idea of Kirchhoff's laws, these are basically common sense laws that we can derive from looking at simple circuits. And in this video, we're gonna work out Kirchhoff's current law. Let's take a look at these series resistors here. There's a connection point right there, and that's called a node, a junction. And one of the things we know is that when we put current through this, let's say we put a current through here, and we know that current is flowing charge, so we know that the charge does not collect anywhere. So that means it comes out of this resistor and flows into the node and then goes across and it comes out on this side. All the current that comes in comes out. That's something we know. That's the conservation of charge, and we know that the charge does not pile up anywhere. We'll call this current I1, and we'll call this current I2. And we know we can just write right away I1 equals I2. That seems pretty clear from our argument about charge. Now let me add something else here. We'll add another resistor to our node, like that. And this now, there's going to be some current going this way. Let's call that I3. And now this doesn't work anymore. This I1 and I2 are not necessarily the same. But what we do know is any current that goes in has to come out of this node. So we can say that I1 equals I2 plus I3. That seems pretty reasonable. And in general, what we have here is if we take all the current flowing in, it equals all the current flowing out. And that's Kirchhoff's current law. That's one way to say it. In mathematical notation, we would say I in, the summation of currents going in, this is the summation sign, is the summation of I out. That's one expression of Kirchhoff's current law. So now I want to generalize. I want to generalize this a little bit. Let's say we have a node and we have some wires going into it. Here's some wires connected up to a node. And there's current going into each one. I'm going to define the current arrows. This looks a little odd, but it's okay to do. All going in. And what Kirchhoff's current law says is that the sum of the currents going into that node has to be equal to 0. Let's work out how that works. Let's say this is 1 amp, and this is 1 amp, and this is 1 amp. And the question is, what is this one? What's that current there? If I use my Kirchhoff's current law expressed this way, it says that 1 plus 1 plus 1 plus I, whatever this I here, has to equal 0. And what that says is that I equals minus 3. So that says minus 3 amps flowing in is the same exact thing as plus 3 amps flowing out. So 1 amp, 1 amp, 1 amp comes in, 3 amperes flows out. Another way we could do it, equally valid, this is just 3 ways to say exactly the same thing. I have a bunch of wires going to a junction like this. And this time I define the currents going out. Let's say I define them all going out. And the same thing works. Sum of the currents, this time going out, I'll go back over here, I'll write in, all the currents going in. That has to equal 0 as well. And you can do the same exercise. If I make all these 1 amp and ask, what is this one here? What is I here? Outgoing current, it's 1 plus 1 plus 1 plus 1. Those are the 4 that I know, and those are the ones going out. So what's the last one going out? It has to equal 0. The last one has to be minus 4 equals 0. So this is a current of minus 4 amperes. So that's the idea of Kirchhoff's current law. It's basically we reason through it from first principles because everything that comes in has to leave by some route. And when we talked about it that way, we ended up with this expression for Kirchhoff's current law. And we can come up with a slightly smaller mathematical expression if we say, let's define all the currents to be pointing in. Some of them may turn out to be negative, but then that's another way to write Kirchhoff's current law. And in the same way, if we define all the currents going out, and you actually have your choice of any of these three, anytime you want to use these, if we define them all going out, this is Kirchhoff's current law. And we'll use this all the time when we do circuit analysis.